In this lesson, we are going to talk about bond enthalpy, how to determine the standard enthalpy of reaction from the bond energies and the lattice energy. First, what is bond enthalpy or bond energy? It is the change in enthalpy that is associated with the formation of a bond from isolated atoms in the gaseous state under 1 atm. For example, here we have an atom in gaseous state that reacts with a second atom also in the gaseous state, and we obtain a molecule in gaseous state. Here we talk about enthalpy of formation of the bond between A and B at 1 atm, and this bond energy or bond enthalpy is different from the standard enthalpy of formation of AB. Here, for example, the bond enthalpy of HCl corresponds to this chemical reaction. We have H in gaseous state plus chlorine in gaseous state to obtain HCl. Here, the bond enthalpy of HCl is minus 431. And here we have the negative sign. For the formation of a bond, it is negative. So it is an exothermic process. But the opposite, if we do the opposite, for example here, we write the opposite reaction. In order to break this bond, we form the two atoms in gaseous state. Here, the bond enthalpy is equal is negative because we have inverted the direction of the reaction, and this we can give it this symbol, dissociation. The enthalpy that corresponds to the dissociation of this bond is always positive. So for example, the bond enthalpy of HCl is minus 431 kilojoule per mole, and the dissociation energy of this bond is equal to 431. So let's do this first example. The question is to calculate the enthalpy of formation of 1 mole of HCl in gaseous state from the bond enthalpies at 1 atm. We are given this thermodynamic data. We start first by writing the formation of HCl from its elements in their standard states. So to form HCl, we need hydrogen gas in standard states and chlorine gas also in standard states to form HCl. Here they are asked for 1 mole, so we need 1 here. So we have to balance this equation. Now to determine the enthalpy, and here we have the enthalpy of formation of HCl, and we will use the bond enthalpies to calculate this energy. First, we have to change these molecules into their isolated state, which means that the hydrogen gas will be decomposed in atomic form. So here we'll have H in gaseous state plus chlorine in gaseous state. So here we have the definition of the bond enthalpy, which says that it is the change in enthalpy that accompanies the formation of a bond from isolated atoms in gaseous states. So here we have these atoms in gaseous states to obtain HCl. But in order to go from the molecule to the atomic state, we need energy, and this energy is given here. Here it is. We have the bond enthalpy of H, which is equal to 436. So to go from this to this, we need to provide an energy that corresponds to the dissociation of this bond. But here we have 1.5 hydrogen gas. So we have to multiply by 1.5 and by minus. We have multiplied by this negative sign in order to have a dissociation. We have said that the dissociation corresponds to the energy provided to the bond to be broken. And because here it is negative, so we have to multiply by -1. If it were positive, we have to let it as it is. So here we have multiplied by 1.5 because we have this stoichiometric coefficient 1.5 times the bond enthalpy of formation. The same thing here. We have provided energy that corresponds to the bond between chlorine. The same thing, the stoichiometric coefficient 1.5 and minus the sign because here we have a negative value. This energy corresponds to the formation of bond between chlorine atoms. And here we need to break this bond. So it must be positive. So in both cases here, they are positive. It must be positive. Now, to go from this intermediate state, here we have an intermediate state, to the HCl bond, we have formed this bond, HCl. Here it is. Now this energy is negative. Why it is negative? Because we have to form the bond between H and chlorine. So it is negative. Now, in order to calculate this standard enthalpy of formation, which corresponds to the direct path, here we have the direct path. Here we have the indirect path. So we apply the Hess law. The Hess law, we have the standard enthalpy of formation. We have the standard enthalpy of formation, which is equal to the sum of all this energy that were exchanged during the indirect path. So we have here minus 1.5 the bond enthalpy in hydrogen, minus 1.5 the bond enthalpy in chlorine gas, plus the bond enthalpy in HCl. So now we have just to replace each energy by its value, which is equal to -1/2. For hydrogen gas, the bond enthalpy is 436, but in minus, negative sign, 436 -1/2. For the chlorine, it is equal to 243 minus 243. Plus, here the bond energy of hydrogen or hydrochloric acid is 431. If we make this calculation, we get a value of 91.5 kilojoules per mole, or approximately 92 kilojoules per mole. So here is the method how to calculate the standard enthalpy of formation for using the bond enthalpy. Now let's talk about the bond enthalpy in polyatomic molecules. And in this case, the bond enthalpy does not depend on the type of atoms. Besides, it depends on the electronic environment. For example, we have this molecule CH4. So we see here the Lewis structure of methane is as it is. Here we have 4 bonds. They have the same energy level. But when we have bonds of different types, for example, in this molecule methanol, like this, here we can see that we have 3 bond CH and 1 CO bond, and we have OH bond. Here we can see that we'll have 3 different types of bonds, and each bond it has its own energy level. Here we call it delta H AB 1, here 2, and here 3. So we have 3 types of bonds. And here also the electronic environment of each bond is different. So when we calculate this type of bonds, we generally neglect the interaction effect, but it is inaccurate because the geometry of the molecule and the interaction between the bonds affect the energy level of the bond. So let's do this example. Here we are asked to calculate the bond enthalpy in CH4 in methane gas. We are given this thermodynamic data. We have the enthalpy of formation, the bond enthalpy, and the standard enthalpy of sublimation of carbon graphite. We start first by writing the thermochemical equation. So to form the CH4, we start from the elements in their standard state. We start by the carbon graphite plus hydrogen gas. Both elements are in their standard states to get the methane gas. And here we have the standard enthalpy of formation of this molecule. And of course, we have to balance this equation. So we have 4 hydrogen. And in order to obtain the bond enthalpy CH, we need to convert each element in its standard state to an isolated atom in gaseous state, as we have seen before. So here we have to get the carbon gas, the atomic carbon gas, and hydrogen gas. But here we have 4 hydrogen gas. So in order to go from the carbon graphite to carbon atom in gaseous state, we need to provide an energy that corresponds to the standard enthalpy of sublimation that is given here. The standard enthalpy of sublimation of carbon graphite. And also here we have bond between 2 hydrogen atoms that we need to break. So we need to provide this energy the energy to break these 2 molecules. So we have to multiply by 2, and we add the negative sign because here we are using the bond enthalpy of formation. And all this will be positive because it corresponds to the bond separation or dissociation. Now we can form the CH bond. That's what we have formed according to Lewis structure 4 bonds of CH bond. So we multiply by 4 varieties. Now, by application of the Hess law, we can calculate the bond enthalpy of CH found in CH4 molecule. By application of the Hess law, we will add all these energies involved in this indirect path. We start by delta H sublimation. We have the standard enthalpy of sublimations of the carbon graphite minus the energy provided to separate the bond between H atoms plus 4 delta H, the energy to form CH bond. Here it is negative because it is a formation step. Now we are asked to calculate this value, which is equal to the enthalpy of formation minus the standard enthalpy of sublimation of carbon graphite plus 2 the enthalpy of that is used to separate the bond in HH, all divided by 4. So now we can replace. We have this, the standard enthalpy of formation of methane gas of methane is minus 74. Minus 74.8 minus 718.6 plus 2 times the bond energy in hydrogen molecule, 436. So everything is divided by 4. And we get a bond energy of 416.4 kilojoules per mole. So here is the bond energy CH in methane gas. Now we'll do the same example but with different molecule. In methanol molecule in gaseous state. Here we are asked to calculate the bond enthalpy of CO in methanol, and we are given this thermodynamic data. So also always we start by the thermochemical equation. To form methanol, we have to start from its element in standard state. We start by carbon in graphite plus hydrogen gas plus here we have oxygen, so we have to add oxygen gas in standard state to form methanol. Here we have to balance the equation. We have here 4 hydrogen atoms, so I have to multiply by 2, and I have 1 oxygen atom, so I have to multiply by 1.5. Here we have formed 1 mole of methanol. Now to this chemical reaction corresponds to a standard enthalpy of formation, which is here given. It is equal to minus 201 kilojoule per moles. Now we need to form the bond in this molecule. This molecule looks like this. It has this Lewis structure. So we need to convert each element to an isolated atom in gaseous state. After that, we will form each bond. So the C graphite is converted to atomic carbon in gaseous state. We need energy that is called the standard enthalpy of sublimation. Also, we need to break the bond in hydrogen molecule. So we need to provide the bond energy H, but we have to multiply by 2, and because it is a formation energy which is negative, it must be positive. So I have to multiply by 2, by minus 1. And oxygen, we have only one oxygen atom here because it is multiplied by 1.5. So here I have to provide energy that corresponds to the bond OO, okay, and I have to multiply by 1.5. And because it is here formation energy, it is negative, I have to multiply by negative to get the dissociation energy. So all this is positive. The same thing here, it is positive. So now I have plus 4 hydrogen atom in gaseous state plus 1 oxygen atom in gaseous state. Now once the atoms in gaseous state are formed, now we can form each bond in this molecule. So according to this structure, we'll form 3 bonds between C and H. So 3. We have also 1 bond CO and 1 bond between O and H. So now I have to apply the Hess law to write the expression of the standard enthalpy of formation with respect to the indirect path. Here we have this thermodynamic cycle. So we add all this energy that are exchanged during the indirect path. And here the question is to calculate the bond in CO in this molecule. So it is this energy that we are going to calculate. The enthalpy of formation of CO is equal to the standard enthalpy of formation of the methanol minus as the final expression of the bond enthalpy of CO. Now we just replace each enthalpy by its value, and we plug all values in a calculator and we obtain the final value of this bond. Here we have the formation bond is equal to minus 201. So we have just to replace minus 26 minus half 100. Here negative. All these are formation. Corresponds to the formation of the bond. Plus 3 minus 416 plus OH, which is equal to minus 463. We plug this value in a calculator and we obtain the final value of the bond energy between C and O is equal to 330 kilojoules per mole. Here's how to calculate the bond enthalpy from the thermodynamic cycle by application of the Hess law. Now, as general rule, we can determine any standard enthalpy of formation from bond energies by application of this expression. We have the sum of the bond enthalpy of the products minus the sum of the bond enthalpies of the reactants. And of course, we have to take into account the stoichiometric coefficient of each reactant and product. And also, if we have a change in physical form, for example, from solid to vapor, to gas, or from liquid to gas, we have to introduce here the parameter of the standard enthalpy of sublimation or of vaporization. Now let's talk about the lattice energy. With ionic solids, we don't use the term bond energy, but instead we use the term lattice energy, which is the enthalpy change that is associated with the formation of an ionic solid from its ions in the gaseous state. So to make it simple, we have an atom or an ion in gaseous state, a positive ion, that reacts with a negative ions, also in the gaseous state, to form an ionic solid. And this reaction corresponds to the energy lattice, which is negative. So in order to evaluate the interaction between these two atoms, we don't use the term bond, but instead we use the term lattice energy. For example, the lattice energy of NaCl is obtained from this reaction. We have the positive ion sodium plus the negative ions in the gaseous state chlorine to give NaCl. And the energy lattice is not accessible through experimentation, but instead we can obtain it from the Hess law that we apply on the Born-Haber cycle. In order to have better idea about the Born-Haber cycle, we'll represent this cycle through the formation of sodium chloride, and we'll apply the Hess law to calculate the energy lattice. We are given this data. We have the standard enthalpy of formation of the sodium chloride, also the standard enthalpy of sublimation, also we have the bond enthalpy of chlor in chlorine gas, the ionization potential of sodium, and the electron affinity of chlorine. So we start first by writing the direct path, which corresponds to the formation of NaCl from its elements in the standard state. The standard state of sodium is solid, and the standard state of chlorine is chlorine gas to give NaCl. But the lattice energy is obtained only from the elements or the ions in gaseous state. So we have to convert the sodium to a gaseous state, and after that to an ion, and the same thing for the chlorine. So we have to convert the sodium to a gas and also chlorine to a gas. Here we have to balance the equation because we have one chlorine in the NaCl. So now, in order to move from the sodium solid to the sodium gas, we have to provide an energy that is called the standard enthalpy of sublimation. And in order to obtain one chlorine in gaseous state, we have to provide the bond enthalpy between chlors in chlorine, but we have to multiply by the stoichiometric coefficient, and also we have to multiply by the minus sign, because here we have this value is positive or negative. We have to multiply by negative in order to obtain the dissociation bond. Now we have formed these two atoms in the gaseous state, but it is not enough. We have to convert these two atoms, these two isolated atoms in gaseous state, to their ions. So we have to convert the sodium in a positive ion. In order to convert the sodium to a positive ion, we have to provide an energy that is called the energy potential of sodium. It is given here. Here it is. It is equal to 496 kilojoules per mole. And in order to obtain the negative ion chlorine, we have to provide an energy which is equal to the electron affinity of chlorine. So these two energies will ionize both atoms. Now we have our condition of the formation of this solid, ionic solid, from its elements in the gaseous states as positive and negative ions. So here we write this. Here we have the energy lattice. And here this main reaction is the standard enthalpy of formation of sodium chloride. Now we have our Born-Haber cycle. It is called the Born-Haber cycle. Now we'll apply the Hertz law to calculate the energy lattice. So we have here the standard enthalpy of sublimation minus 1.5 bond energy of chlorine plus the ionization energy of sodium and the electron affinity of chlorine, and at the end we have the energy lattice. Now it is easy to obtain this energy which is equal to the standard enthalpy of formation minus standard enthalpy of sublimation minus half the bond energy of chlorine plus the ionization energy or potential plus the electron affinity of chlorine. Now we replace by their respective values. We have for the formation of NaCl is equal to minus 411 minus the standard enthalpy of sublimation is equal to 109 minus 1.5. The bond enthalpy of chlorine is minus 243. The ionization potential of sodium is equal to 496. And the electron affinity of chlorine is equal to minus 348. So now we just plug this value in the calculator and we calculate the value of the energy lattice. Minus 789.5 kilojoule per mole. So here is the method how to calculate the energy lattice through the Born-Haber cycle. And the difference between this Born-Haber and the other cycles is that here we have other energy that are involved, that are the ionization potential and the electron affinity of the atomic species in order to be converted to ionic species.